Okay, so we are live on YouTube now, and
Okay, okay.
I think Siddharth, you can hide the bar like by clicking the hide button.
Yeah, sure.
Yeah. Okay. So yeah, let me introduce you. So welcome everyone. Today we have Siddharth Prabhakar from Dassult System with us. So he's presently working as an industrial process consultant at Dassult System India. He's actively working with electric vehicle OEMs and startups by helping them validate their EV data and incorporate best practices in their design. He also works on developing innovative multidisciplinary solutions that can help customers save valuable time and solve their problems. He has knowledge in 3D modeling, structural and thermal simulations, and 1D simulations. He has been working with Dassault from the past 1 year, mainly on CATIA and Simulia apps. So, welcome Siddharth Prabhakar for this intensive, interesting session, where both the students who are shortlisted for the first under the first shortlisting are also there, but you are also live on YouTube, and I'm sure your session will benefit thousands of engineers through YouTube videos that will be relaying live and later on. So welcome, Siddharth. The stage is all yours.
Thank you, Dr. Beavis, for the introduction. So, good morning to all of you present here. So, in today's session, what we'll be, uh, just a second, I'll just change my, yeah. So, in today's session, what we'll be mainly focusing on is the structural simulation aspects and thermal simulation. And post lunch, we'll be also doing the 1D simulation aspects on the Daimola tool. So, feel free to stop me in the middle if you have any doubts during the presentation itself. So towards the end, we'll also be working on a hands-on model. So I
Uh,
hope, hello.
Siddharth, I want to mention something. So we have
Yeah.
not allowed student to unmute themselves, but they will be
Okay, okay.
writing a chat message. So what we felt that earlier speaker have followed the trend because your session is long. So every
Okay,
30 minutes they will stop and browse through the chat messages in order to accommodate their queries in between.
okay,
Do
okay.
you,
Yeah,
do you
that should
want,
be helpful too.
yeah,
So
in case
Lloyd
you
could
want
help
me,
me with that.
okay, okay, fine. In case you want them to talk, I can allow them also, whatever you
Okay.
prefer. Okay,
Sure, anything is fine. I mean, as long as if they have any doubts, they can either put it on the chat box or anything is fine by me.
fine. I'll monitor it. So all students, if you want to have a like voice-based conversation, just raise your hand. Otherwise, write your message in the chat box. Thank you.
So before we start with the session, I just want to confirm that if the students have downloaded the required applications that we'll be working on in this particular session. So I'd shared a document earlier on Friday evening where the applications were mentioned. So if you have downloaded them, just have it. If you haven't, then you can go through the document and keep them downloaded too. Yeah. So let's start with the session. I'm just, yeah, actually, Lloyd sir is trying to connect with me. I'll just quickly mute myself and come back. Oh, yeah, sorry for the disturbance. So let's start with today's session then. So what we'll be mainly focusing on is structural simulation. And today's agenda will be introduction to the Simulia brand, then the user interface and commands. We'll be also focusing on the meshing aspects, that mainly is the types of meshes that are present for a model. Then we'll be creating and assigning the mesh properties to geometry. So how is that done is I'll be showing you that too. Then the material aspect. So why is a material important in a simulation model, and how do we create a material on the 3D experience platform, and then defining the material properties. Then we'll be setting up a basic simulation scenario wherein we'll be just finding the mesh properties, the material, just to see how the whole process goes through. And then we'll be defining the loads, restraints, and initial conditions for our model. And after that, we'll be defining the interactions. That basically means the contact that the model has, the product has basically. And then finally, we'll be doing the hands-on session. So coming on to the introduction of Simulia. So Simulia basically is a brand from Dassault Systems that mainly focuses on multi-physics simulations. So the solver that it is based on is Abacus FEA solver. So it's one of the best solutions in the industry currently that we have. And the tagline for Simulia is "Reveal the world we live in." So before we go into a little bit more detail about the Simulia brand itself and what all products it has in its portfolio, let's understand a little bit history about it. So Simulia brand was established in the year 2005 after we acquired the Abacus FEA solution. And after that, there's a diverse range of products that we have included in the Simulia portfolio. So you have various products from your platform application to your standalone applications. So this is how the whole Simulia brand is. You can see in the graphic shown here that the different tools which we have, it's Tosca, SFE, Simfo, FEA Safe, Simpax. So there's a lot of tools like this serving all of these industries. So coming on to what Simulia, the capabilities that Simulia has and the type of simulations that it can handle are basically structures and durability, electromagnetic simulation, then multi-body system simulations. We also can handle fluid simulations, vibroacoustics, automation and optimization, and optic simulations. So these are just a few that we have mentioned, but there's a lot more that you can do with the Simulia tool itself. So coming on to why do industries want to simulate their models? Why don't they rely on still physical testing? And why do they invest so heavily into the virtual models itself? So I'll be taking you through a basic water bottle example as to what all is done during a water bottle example and the water bottle simulation and what type of simulations can be done. So why this is done is basically to evaluate the product's behavior in real life. So without actually needing to physically test, since it's not like one or two tests that you do, it's like a lot of tests that you do in order to finally manufacture your product. So all of this can be avoided by using the virtual tools. So that is one point. Then we have to optimize the products, that is to increase their performance, their life, and to validate their weight characteristics. So this is one more very important point that we can do. So instead of having a design to be physically tested, then a change to be done, and then again to be physically tested, we can just optimize their performance on the tool itself. And these simulation models also help in guiding engineering decisions by basically providing high fidelity virtual models, which help in guiding these engineering decisions too. And all of this, that is to evaluate, to optimize, to guide these decisions, all of this can be done by understanding the behavior of materials in real life, that is with the environment, and how these products are going to interact with the environment. So for example, it's a water bottle. So you'll have to manufacture it, fill it with a fluid, then ship it into a container. It has to travel to different countries. So all of these situations can be simulated on a virtual environment itself. So now that we have cleared the yeah, so how do we do this process? Is basically, if you can see the first image is basically of the water bottle, that is our product. So then we create a reference model for it. So a reference model is exactly a 3D model of the given product that we have. So the 3D model is designed on one of our CATIA applications. And once you design the reference model, we go on to creating a simulation scenario wherein you'll be assigning the mesh properties, you'll be assigning the material properties, you'll be basically setting up the whole scenario for all of them except for the what particular simulation are you trying to do. So once you have the simulation model ready, what you'll be doing is selecting a context. So context is basically what type of simulation do you want to achieve. Now, it could be either a structural simulation of the product, or it could be a thermal simulation as to what amount of heat or the cold properties that are going to be transferred to the fluid inside. Or maybe you could just do a fluid simulation of the fluid that is inside the bottle. So it could be anything, and there's no limit to it. Based on the simulation scenario, you can use these tools and you can set up a scenario. So once you have selected the scenario that you want to simulate, you can go on to the solver, which is the Abacus FEA solver, and you can finally simulate your model and validate your results too. So the validation is basically trying to achieve the results you have results you've actually defined while defining the requirements. So that is where you can validate your results. If there's any issues, then you can reiterate it and again try to validate your results. So this is how the whole simulation process looks like, and the Simulia portfolio has all of these applications in it. So starting with now that we have covered the whole simulation aspects, we can go on to how simulation is done on the 3D Experience platform. So why is 3D Experience platform so important is because it provides a single interface for all of these components. And as you already have seen that how the 3D Experience platform has the capabilities of handling multidisciplinary solutions. That is from you can model a given product, you can simulate it, you can do the result analytics, and there's a lot more you can do on the 3D Experience platform itself. Now, one more thing that the 3D Experience platform does is it combines all the brands that Dassault Systems has. That is from your Ketia, Innovia, BioVia, Simulia, Delmia. So all of this are present in one single platform. So what this helps us in doing is it helps in seamlessly transferring data among all of these applications. So if you have a product, you have modeled it on the same environment, then instead of having to export it and then again import it, what you can do is you can just shift the application, go on to the simulation apps, simulate on the model. If you further want to optimize, you can use our optimization tools like Process Composer or parametric design study applications, and that further you can do all of it on the same environment itself. So this is how the 3D Experience platform helps you. Now, I'll just take you through basic commands that are to be followed in order to generate a simulation. But here we'll be focusing on the input, export, save, share, and all of these commands. So how do we create a new content? So based on the application that you're a part of, if you press the plus icon that is present there, so once you press on it, you'll be having an option for new content. So the new content will help you add any of these contents for your given product that you want to work on. So in respect to simulation, what you will be doing is you can add material properties such as core material or covering material. You can create a new simulation process, or you can add a physical product on which you're going to do a simulation itself. So these are a few options that you can use directly from the new content, or you can go on the 3D Compass and access the application from there itself. The next command is save and share. So save, as the name suggests, it's basically saving the progress which you have done on a model, while share is quite an interesting option because it helps you share your progress with your co-workers, or maybe if there's any progress or any ideas that you have with your product, you can directly share it on the swim communities. So this helps in better collaboration and better understanding between the co-workers itself. Then we have the import and export option. So for importing a file onto the 3D XML format, mostly it should be in a 3D XML file formats, or it can be a SolidWorks file. For simulation, we have multiple file formats. Again, if they're coming from different softwares. So if it's an Abacus file, then it needs to be a .inp file format. And also you can import the neutral format files, that is IGS and step files. Also, since we have CATIA V5, so CATIA V5 products can also be imported onto the platform. So it can be seamlessly done by importing a .catpart file. So if you can see the blue circle, which is on the first graphic, so if you press on that arrow there, you can import a CATIA file too. Now we have export. So export from the platform will be in 3D XML format itself. So the 3D XML file will be how it is exported. But for again the simulation aspects, it will be the .inp format or any other formats that are present there based on the application that you're trying to use it into. Now, one more thing that we have added on the Simulia application is the assistance command. So what this does is the assistance command gives the user a complete set of steps that the user has to follow in order to achieve a simulation. Now, what the user can do is start with the modeling, then go on to setting up a step for it. It can be a quasi-static step or just a static step. Then the user will have to define the initial conditions, then define the boundaries, the contacts, and then finally the mesh properties and materials. So the assistance will give a error or a warning message if one of these steps hasn't been completed. So for somebody who's just starting off with simulation or needs any help by the tool itself, so the tool has this option where the user can get assistance from. So coming on to the benefits of the 3D Experience platform. So it basically helps to collaborate in terms of CAD, mesh, and simulation objects. Since, as you already know, all of this is present in the same environment. So anybody who has access to a given content or a product can use it and make any changes. And all of this can be traced back. So the traceability on the platform is again very good. So any changes that have been made can be traced back to the user who has done it. Also, this particular the 3DEXPERIENCE platform helps you in automating your meshing and the modeling aspects. So if somebody is, for example, a design engineer who does not have a lot of knowledge about simulation, but still wants to validate their progress, can maybe just use an automated meshing aspect and the material creation will be automatically done too. Then the platform itself, since it is cloud-based, it is efficient in handling large-scale and detailed models. And the solution at the backend solves the simulation is Abacus, which is the best-in-class solution. Then collaborating work on CAD, since the design engineer and structural engineer can collaborate much more easily. So they can go back and forth between the changes. So the structural engineer can simulate and validate the results and tell the design engineer if there are any changes that are to be done. And all of that can be done on the same platform and they can collaborate very easily instead of having to export and import the files again and again. Uh, so since the whole process of a simulation or any modeling in that aspect would be a lot tedious to somebody who's just starting off. So we have a lot of options where you can find help from. So instead of going and connecting with your manager or your senior for any basic doubts that you have, what you can do is you can use these commands for your help. So starting with the first one is basically on your keyboard, you can press the function and F1 key. If you hover upon any command there on the tool and you want to know what it does and how you can use it, you can just press function and F1 and it will give you a short brief about what the command is used for and how you can use it for your product. But if you need a more detailed explanation, then you can go on to the question mark icon, which is present in the top bar, which will give you a detailed explanation about how exactly these tools work and what all can you do, and a little bit background about them too. So this will help in a more detailed understanding. So this is not restricted to only your tool, but everything on the platform from setting up preferences to changing your design layout and your preferences settings. So all of that can be done and the user guides could help you with that. And also we have User Companion, which is basically the 3DEXPERIENCE edu space. So this has a lot of courses and contents which a user can go through and try and understand a given problem, a given program software itself. So if it's CATIA you are trying to understand, you can go and search for a CATIA course. You will have all the models which you could work on. You can understand the details, and this could really help you in understanding an application or anything that you're trying to achieve. So it has all audio, video, and hands-on content in it itself. And finally, in the end, if all of this you could not do and you're still having your doubts, so what you can do is we have a lot of swim communities. And in the last session, we already know the benefits that these swim communities have. So for Simulia, we have a Simulia user community where the students or anybody has any doubts can just maybe take a screenshot or write it in a para and ask their questions on the community itself. So the experts all over the world who read them or your co-workers who read them can directly put their views on the comment section, and that could really help you with going forward with your activity which you're working on. So now that we have covered of how the 3DEXPERIENCE platform can help you and the benefits that the platform has, the helping aspects and everything, we can move on to actually working on a simulation product. So to start with, in a simulation, what we do is we create a mesh initially. So a mesh is something, basically you discretize a geometry into many small geometrical shapes. That is a finite elements you discretize the main geometry into. Now, in order to use the FEM type of a simulation, you'll need a mesh property defined that is for the finite element process. If you can see the image which is shown here, the blue object is what is your product, and the black lines which are dividing this given product into multiple sections are your discretization into finite elements. Sorry, yeah. So this is how you do your meshing aspect. Now, one more thing meshing is, so the discretization into small elements could be of any shape. So the main shapes which are usually followed is triangles, quadrilaterals, tetrahedrals, and hexahedrals. And if it's a higher order simulation that you're trying to achieve, we have quadratic and linear tetrahedral elements. So any of these commands, if you're a little doubtful, you can use the help option to understand what they are used for. Now in meshing, based on the product, the mesh size and the mesh properties are different for each part in a product itself. So if you can see the image here, the mesh for the outer body is a little different, but the inner cavity which is present there has a much more detailed mesh as compared to the outer. So you do this when you're maybe having a stress concentration zone. That is, if you have a, a sharp corner in your object, so that is where you can define a higher stress. Since the stress concentration would be higher there, you can define a more finer mesh, and this will help you get your results much more. You can validate your results much more easily there. So when you create a mesh product on the 3D Experience platform, there is a component called FEM representation that is created on your specification tree itself. So in the tree, you will have your type of mesh which is defined for for a product, and you'll also have the properties such as the solid sections, and all of them also defined under the FEM representation itself. So it will be a separate entity in your specification tree. The other thing which you have to note is if you're trying to create a mesh, it will only be either for a 3D part or a physical product. You cannot create a mesh for a surface. Like just for a surface, you cannot. You'll have to select the part of the 3D product on which the FEM will be created. And also you can create multiple FEM representations for a given product, but while doing the simulation, only one of these FEM representations will be used. But you can go back and forth between them to validate your results and to iterate the process multiple times. So this is about the meshing, basics of the meshing. Now, how do we create a mesh on the 3D Experience platform? So I'll just take you through the process a little bit. Towards the end, we'll be doing a hands-on, so I'll again be explaining you all of this. But right now, you can just view as to how this mesh is created on the platform itself. So to create a mesh property, you'll have to go onto your on your compass, and you will have to search the structural model creation app. So this is a part of the simulation engineer role. The structural model creation app is present. So once you search that and you open it, before you actually start working on the application, you will have a pop-up that comes there. So the pop-up will basically ask you what to initialize the support as. So you could either select main bodies, all geometries, or select a few geometries out of your product itself. So the default by which it is selected is main bodies, and that is what we'll be going ahead with too. But if there's a specific situation or if there already been meshes generated, then maybe you can use all geometries or selected geometries on which you can do the simulation. Now, again, there's one more option for initializing the method of the mesh process itself. So you have different methods there. So you have none, you have automatic, manual, rule-based, and procedure-based. Now we'll be seeing a little bit more about them as to what each of them are. So none is something, if you select a none option, that is once you select none and press OK, you'll be entering your physical product on which you're trying to mesh. There'll be no FEM representation that will be created on your tree. So you'll have nothing. So you'll have to create it by yourself. You'll have to go onto the action bar, press on the command, and that's when you'll be able to open it. But if you select automatic, the automatic will automatically generate a FEM representation on your tree. And for solids and volumes, it will assign a tetrahedral mesh, while for surfaces, there'll be a surface triangular mesh that will be assigned. You can change the properties by going into each of these meshes, but the automatic command does it all for you, and the mesh size and the mesh stack is initialized from the geometry itself. So this is for somebody who's just trying to have their results validated a lot more faster than to follow the whole procedure. But this is a very helpful command for somebody who's just starting out with simulation. The next we have is manual. So in manual, what you do is you can select a given type of a mesh for all of your geometries. So for example, if you have a cube, two cubes in a given physical product, then you can select the mesh type. So the three mesh types which you can select from are octree tetrahedral mesh, then you have tetrahedron mesh and sweep 3D mesh. So once you select out of them, the mesh properties for all of the components will be assigned the same, and the mesh size and sag ratio will be initialized from the geometries, or you could give it from here too. So this is the manual initialization method. Next, we have rule-based initialization and procedure-based initialization. These are for much more industry point of view. So what a rule-based initialization is, you give an input file where the mesh properties are already defined, and the product will be following those mesh properties itself. So for example, if you're working in an industry and on a particular product, where the mesh properties have to be standardized and a particular type of standardization is followed, then in that process, you can just import the file which is there. So there's multiple file formats available. So you can select that, and that particular rule-based import will be done for the initialization of the product. Again, procedure-based is something on the similar lines, but here you'll have to give a set of initial Visual Basic script, and this will be used in order to generate the mesh onto your physical product. So these two we won't be talking about them much, but these are two very important mesh initialization which are usually followed in the industries. Now creating an in FEM, so creating an FEM representation. So upon initialization, the 3D Experience platform not only generates the mesh properties for you, but it also, so apart from selecting none, if you select none, none of it will be created. But if you select the other ones like automatic or manual, then you'll have the representation automatically being created into the tree. So there's one more thing called as section properties. So properties will be created, but the material properties are not assigned, since for section properties, materials are the base on which they function. So you'll have to define the materials. But in this case, it will create the representation, but you'll have to just go and select and enter the type of material that you are using. So if you're selecting none, then no 3D representation is created in the tree. The mesh paths are not created, the section properties are not created, and you'll have to pick them and choose them from the action bar itself. So you'll have to do it all manually. This is what the none command is. Now, again, in FEM management, there are two types of workflows that exist on the 3D Experience platform. So one is meshes of assembly and assembly of meshes. So I'll explain a little bit more about them, what exactly they are. So in meshes of assembly, you will have one global FEM representation. So for example, if you have an assembly with multiple parts in it, so once you do a generator mesh for it, the FEM representation is created at the global level. So you can see the first graphic there. You can see that the arrows are pointing to the global level FEM. So there's no individual part level FEM representation that is created. The FEM for all of these components will be present at the global level itself. So this is what meshes of an assembly are. While on the other hand, assembly of meshes is basically each of these individual parts in an assembly will have their mesh properties already defined. So you don't really have to go and define your mesh properties again in your global FEM. So what it does is the FEM representation that you have in your part level are directly linked. So it's not created, it's linked to the global FEM. So there's a link between the part level FEM and global level FEM that is done. So this is what assembly of meshes means. So a little bit more about meshes of assembly. So in order to select which components at the global level the FEM has to be created, the command you'll be using is contributing shapes manager. So you don't need to remember everything. We'll be doing this on hands-on as well. So all you could just try and understand what these commands do and how they help you. So the contributing shapes manager. So what you will have to do is, as you can see the image, the second image has a main physical product that is connecting rod assembly. And the multiple parts which are present in that assembly are shown there. So the check icon, so if you uncheck any of these parts, for example, then that will not be selected in your main product. So once you select all of it, the whole product will become green in color. So that means all of these FEM representations will be present in the global FEM itself. So this is what the meshes of an assembly does. While for assembly of meshes, you use the contributing finite elements model manager. So it's just two options beside the earlier command which we saw. So here what you can do is, since you'll be creating a global level FEM, but the FEM of individual parts will be linked to the global one. So you can either create a new FEM at the global level, or you can use the existing FEM itself which you have. So it gives you an option. So you can create a new one either on directly on the fly itself. So you can just initialize or complete with a new FEM, or you can use the existing FEM too. So just for a little bit more explanation, so the same assembly which is connecting rod. So you can see that in the contributing FEM representation, in the second image, you can see that two of these items are green in color. So if you reuse an instance, that is, if you reuse an existing FEM that has been created in a part, then you can use the reuse command. But if you want to create a new FEM, then you can create a new FEM and it will be linked to the global FEM. So this is how the assembly of meshes command works. Now, a little bit difference about this. So as I've already told you, the first difference which is shown here is the global FEM and how it is different for both of them. Now, one more thing to notice, when to use which. So meshes of an assembly is usually used for a component that is not complex. So it does not have a lot of geometries into it. So why we do this is because, for example, if you consider the connecting rod example itself, so you will have multiple products in it, so about 5 to 10. So if you create a mesh at the global level for each of these individual components, so you'll in your specification tree, all you can see is the tetrahedral mesh has been created. You can rename it, but you'll have just the mesh property that is being shown. So if, for example, you need to do any changes, it'll be a little bit confusing if you haven't renamed them. And for a large product with thousands of products in it, it's not possible to rename every one of them and to select and to go back and do any changes. So it's not recommended for a complex geometry or a geometry that contains a lot of parts in it. On the other hand, an assembly of meshes could help you with that, since the mesh is present in the part level itself. So if you have an example wherein you have a lot of bolts, so if your physical products are named as bolt 1, bolt 2, bolt 3, their mesh properties will be defined inside them itself. So you don't need to go at the global level and check which particular mesh is pointing out to which element. So this is where assembly of meshes is helpful. But again, the efficiency of assembly of meshes is not very good in a component with smaller objects and with smaller number of parts. So it's usually recommended for large geometries, while meshes on assembly could be used for a small geometry. Now the mesh creation app UI. So once you open your structural model creation app, you'll have an option to switch between the model and the mesh itself. So the graphic which you can see here, if you press on the drop-down menu, you will see model and mesh. So to mesh any of these components, you'll have to go onto the mesh window. You'll have to select the mesh option from there, and then you can mesh your given components to. Now inside the mesh itself, you have multiple selections from where you can create your mesh. So if you can see the first graphic on the left side, which is mesh, you have different types of mesh that you can create. Maybe it could be a tetrahedral hex mesh, you could have a sweep mesh. There's multiple options that you can select from. While setup, on the other hand, will be the two types of the assembly of meshes and the meshes of assembly commands are present there, and a lot more of them are there. Similarly, operate and display. The display will be where you can display the type of mesh, you can have the display settings change. And group is something where you group a given set of items on which the same properties are to be applied. You can just group it all of them together and apply a given mesh or any of the property, and all of them will have the same properties for them. And check command is for checking the mesh quality that you have created. So you can check the mesh quality and you can see if there's any errors or any warning messages that the tool is showing you, and you can do the changes accordingly. So finally, the action bar looks something like this. You have all of the commands there, and below are the tools which you could use for your mesh creation itself. So again, in mesh, you can import and export a mesh. So if you're somebody who's following a standard mesh, you can import it. You can import a file. And similarly, what we spoke about the rule-based one, you can either follow that approach or you can import a mesh itself. And coming to the export mesh, so we have quite a few file formats in which the mesh can be exported. So you have XML, you have the .inp file format, you have CSV. So there's a lot of options there based on the use which you need. You can export the given mesh into that particular file format. Now, if one more thing that we have to see is updating a mesh. So what happens is if, for example, you have a physical product and you have done any changes in your model. So if you have maybe changed a shape of a given part in your product, so how do you know if the mesh has been updated or not? If you can see the first graphic, it has a yellow color symbol to the end of it. So I'll just point the mouse to it. So this is the command which shows that the mesh needs to be updated. So it basically shows that a change has been done and you need to update the mesh property. So either you can use the update command on your action bar, the mesh will be updated, or you can use the check finite element model and the update will be done before it checks the quality of the FEM that is generated. So these are the two ways you could use, or you can just right click on the model and update the meshes. So any of that can be followed. Yeah. So before we move on to material, if there's any doubts or anything that one needs, they can put it on the chat box, or if they want, they can unmute and ask too. So I'll wait for around a minute, and if there's any doubts in the chat box, you can let me know. Yeah. Dr. Dheeraj, are there any doubts at this point on the chat box, or are the students good to go? Hello. Okay, so I can see a few doubts. Okay, so one of them is the difference between SolidWorks and CATIA. So both tools work on the same aspect. So you'll have the design part there. It's just that the levels of detail that you can do for a model are quite different among the two softwares itself. So if you try to dig in more deep, so you have a lot more commands in CATIA or a lot more benefits that SolidWorks has over CATIA. So there's a pro and cons in both of them. So there's end of the day, both of them are for modeling itself. Same question. Okay. How the Abacus solver solves the tetrahedral mesh and how it deals with the nodes and elements to solve the model. Solver solves the tetrahedral mesh. Also, there are multiple ways it solves it. So we can go a little bit more detail, or you can go into the help command and see of how it is done. So we'll see if it's part of our this thing, and I'll explain you it then when we are trying to work on the model itself. And yeah, I think that's it. So if there are any other doubts, you can maybe post it on the swim community, and we could answer your doubts there too. Yeah. So coming on to your material aspects, now that we have defined the mesh properties and we have understood of how to do them, we can go on to defining the material properties. So what a material does is it captures the physical characteristic as well as the visual appearance of a given product. So your material characteristic is basically basically captured by a set of material domains. So your material domain could be a simulation domain or appearance domain. So based on that, it is captured. Now, what a simulation domain does is it basically contains the physical characteristic, while the appearance domain mainly has the visual characteristics to it. So coming on to the next one. So we have two types of materials. So we have a core material and a covering material. So core material is something which is the material out of which the component is made out of, while the covering material is something which is used to cover a given material. So for example, if you're applying paint to a given product, that is what the covering material will refer to. Now, one more thing that we have to notice, only one core material can be assigned to a given product. You cannot have multiple core materials. You'll have to assign only one core material. While in the case of covering material, you can apply up to three covering materials over an object. So in an industry, if you see, for example, your automobile itself, it's dipped into multiple layers of liquid, and different layers are coated. One may be a anti-rust layer, one could be a protective layer, one could be the paint layer. So you can use the covering layer for those particular applications. And if you have created a core material, for example, if you have a metal pipe, so you've already created the metal pipe, you can create an appearance, you can create a covering material over it. That means if you're painting your metal pipe with a given paint, you can use that as the covering material too. Now, how do we create a material onto the 3D Experience platform? So there are multiple ways to do that. So I'll show you the four ways which are mainly followed. So starting with the first one, a material can be created from the top bar itself. So as I had earlier shown you, the plus icon, if you click on it and go on to new content, So you'll have to either search for the material option or it will directly be shown there if you have selected them in your favorites. So you can go and select a core material and a covering material. So once you select them, you'll directly can create a material, assign the domains, and all of that can be done. The next process would be to use the material definition app. So there's a specific app to create a material itself. So you can go onto your 3D compass, search for material definition, and you can open the material definition app itself. So once you open the material definition app, you can go, so one material is automatically created. You can just go and select which domain is present. So if it's a simulation domain you're trying to change, or the appearance domain. And once you're inside the app itself, this is the third way. If you're inside the application itself, you can just go and in the action bar of the given application, you'll have an option to create a material. So you can go and create a material, and if you can see the second graphic, you can select the domains. You can select if there is a covering material to it or not. So these are a few options that you could use. And if you are in the structural model creation app, then inside the app itself, if you have selected none as an option, or any of that for that matter, a material. So in the action bar, you can go and create a material. I think in the properties section, the similar option as it is in the material definition app, you can use it here. You can create a material and then apply it to your product too. So these are quite some 4 ways of creating it. So while doing our example, I'll also show you the methods again. So just keep a note of it that this is how a material can be created on the platform. So what is a simulation domain? We'll just dig a little bit more deep about it. So simulation domain basically captures the physical characteristic. Now, what that means is, now again, the material characteristic is basically a set of behaviors that you can define inside it. Now, for example, if you have a component that is being loaded below their yield point, then in that case, the behavior will be completely elastic. But if you have a component that enters the plastic state, that is, if you load it above the yield stress, then it will enter into the plastic behavior and a deformation will occur in them. So in that case, you'll also have to define the plastic behavior for the material. Now, how do we do that? Is basically once you create a material, you have this particular simulation definition, simulation domain window that opens up. Now here you can either select the elastic behavior by just selecting the elastic command. In this example, what we have is we have created 2 behaviors. So for a material that follows only elastic loading, we can just select the elastic compo reference out of there, and you can define the Young's modulus and the Poisson's ratio, and accordingly you can just do apply the material on your component. But if you also want to do it for an elastic plastic, so you can just rename it to anything. But in that case, you'll also have to select the plasticity behavior and you'll have to define them too. So this is how you can define in a simulation domain. So one more thing that we have to notice, at least one behavior should always be active in a simulation domain. So you definitely need to have a behavior that is defined. So either it's elastic plastic, with hyperelasticity, viscoelasticity, or anything, but you need to define one behavior for sure. Now, also there's one more thing to notice. You cannot have two different types of behaviors assigned to it. So I'll give you an example of what they mean. So two completely different types of behaviors cannot be assigned. So if you can see the example, so elasticity and hyperelasticity are two different properties itself. So for a same material, these behaviors cannot be applied together. While on the other hand, you'll also have to for sure define multiple behaviors in order to get a behavior. So for example, viscoelasticity. So in order to give the viscoelastic behavior for a given component, you'll have to enable the elasticity or the hyperelasticity. And similarly for the plasticity too. So without defining the elasticity component or the hyperelasticity, you cannot define the plasticity value too. So these are a few tips that you could follow. Now a little bit about the UI of the simulation domain app itself. So the plus icon is used to add a behavior. So you can basically add a behavior using the plus icon. So multiple behaviors can be instantiated there, while the cross icon is used to delete a behavior. So if you, for example, created a wrong behavior, if you want to remove it, you can use the delete option. And set as default is setting a given behavior as default. So that is one more option. If you want to switch between different behaviors, you can use the command which the second graphing is pointing out to. So you can switch between different behaviors itself. And okay, so that was about the behavior aspects. So for each behavior, you could create a different domain itself, a different behavior itself. But there's one more way which you could follow. So for example, if you want to try out two different elasticity values for a given component, what you can do is any of these references that you see, we'll consider elastic, for example, here. So you can just right click on it and duplicate. So duplicate will create one more instance of the elastic component itself. So for one, so you can have two behaviors, one with one type of elastic property and the other with other type of elastic property. So this is one more way where you can have two different properties for to iterate your simulation process itself. Now, once you've created your material, now that you have to apply it, now how do we apply it is basically there's an option for material palette. So either you can go onto your 3D search, you can search it and directly drop the material onto your component. But one more simpler way, since if you are an industry and you have a lot of people who are working on the same platform, searching one material is a little hard. You can use 6W tags for it, but it is a little hard to search your material out of the all of these different instances that are present. So what you can do is instead you can just go onto material palette and you have three different options there. So if you can see the first graphic, you have all recently applied and in session. So all will have the every material that has been created and the existing standard ones in the database. While recently applied will be the ones you commonly use it, and in session is the one that you've created in your given session at that time. So you select in session, you can go in your material, select it from there, and you can just drag it and drop it to your main component. So all you have to do is just drag it and either drop it on a 3D part or on a mesh. So you cannot just drop it anywhere. You can either drop it onto the part geometry or on this tree, you can go and drop it on the physical product. So this is how you will be applying the material, and yeah, this is how you can apply the material, and you can there'll be a tick mark that comes in the end and you can just press on it and you will have your material properties assigned to your given component. Now, once you have done your material properties, as I told you, there's something called as section properties that need to be defined. So section properties are basically additional dimensional information that are necessary in order to do a simulation. So for a section property, a material is important. So you need a material property in order for your section command, the section property command to work. Now, if you create a none option, if you initialize it by none method, there'll be no section property that is created. There'll be just a properties command and you'll have to manually go and select the type of section you have. But in case of automatic and manual, you will have a solid section already created. All you need to do is just go and apply your mesh, the type of material that you have used. Now, coming on to the different types of solid sections, it's different types of sections. So you have solid section, you can define a cell section, a beam truss section, SPH particles, gasket property, meshed core. So there's a lot more options that you could use from based on the product that you have. So once you select a given type of a section, for example, it's solid section that we have selected here. So if you can see the items that you will have to instantiate is the support. So support could be the part body on which you're working on. So you can select the part body and just cannot select anything again. You'll have to select the part body. You cannot go and select a surface for which a section is defined. You'll need to select the part body in the specification tree. And then you can define the material such as copper is defined for this example. If it's a different type of section, for example, shell section, then in that case, you'll also have to define the thickness for the shell too. So based on the type of sections which you use, there are multiple data inputs that you'll have to give in order for those sections to work in your simulation model. So how you can apply the material in a solid section. So if you have the product already with the material defined, then the material will automatically come into the material place. But if you haven't defined them and you're going to define them later on, you can just select the magnifying glass option which is there. And you can go and select the material which you have from in session or the recently applied or all. So if you're using standard materials, you can go and select an or all and you can select your material. And then your material will be applied to your given solid section too. Again, there you can import and export your materials. So the import will be either a .inp or a .3DXML file. So that's how you can import a material. While importing also, you have the option to change the units too. So you can change the length, mass, so all of these properties can be again changed for the material definitions. And for export, if you have created a material and you want to export it, it will be a 3D file formatted. So there's, I think, no other options that are provided. It will be a 3D file format. So this is how basically you define your meshes, your mesh properties, your section properties, and your material definition. Now, to do all of it on one single product, that is what we'll be taking a look at now. We'll be defining each of these individually for a component. So I'll take you step by step through a process which is done here. So what you first do is you create a new content. That is, you import a given geometry. So you go onto your plus icon, click on it. You go on to import, and if you have a physical product in your this thing in your system itself, you can just import it from there, and you'll have to import select it from wherever it is on your system, and you can import it as a reference or as a new. If you want to do any changes with it, you have to do it as a new, and you can duplicate string is basically it'll put a string. That is, if you put my name like Siddharth and a product. So the product which will be created in your document will be the Siddharth cantilever beam. So that's how you can do it. So you can either use your name or you can give a standard name which is being followed, but that's how you do it. It's recommended for as a new since you can do any changes on your model too. Now, once you have imported, if the import is successful, you will be seeing a pop-up window like this, which will show the status to succeeded. And now that you have your model, you'll have to open this. So right now it's on the product finder application from Innovia. So you'll have to just right click on it and click on open. So there's multiple types of open that you can do. You can do a smart open, advanced open, but a little, those all are not that important at this point. You can just use the open on the first pop-up window that is there. You can just use the command from there. So once you open it, it will again give you, so for open advanced, this is what you will get. But if you just open it, you can directly see your product and the given application which you want. And once you have the product now that we have the physical product, now we can start generating a mesh on it. So you'll have to go to your 3D compass, search for the given application, which is structural model creation application. It's a part of the simulation engineer role. So once you open the application, it will give you the type of initialization method which you want to follow. Now, as I've already told you what each of these methods mean, you can either select none, automatic, manual, rule-based, or procedure-based. So here we are going to select automatic. And as I've already told you, once you select automatic, the FEM representation is automatically created into your specification tree. So you don't need to go and again create the FEM representation, it will be automatically there. So now how do we create a mesh? So if you can see the drop down arrow, which is there in the down, so you can just click the arrow and you can go on to the mesh creation app. So once you click on it, now you'll be inside the mesh UI. So the mesh UI will have all of the commands and everything on the action bar. So we can create a mesh for the given geometry. So we'll create tetrahedral mesh. So tetrahedral mesh, you can select it either from your component, from your main 3D geometry itself, or you can select from the specification tree that is part body. So any of these methods can be used to select a given component. And then what you can do is you can define the mesh size and the mesh sag. Now, if you're somebody who's not familiar with these terms, you can just initialize these properties from the geometry. So you really don't need to define them. The tool will do it for you from the geometry itself. And the element order, so you have a linear element and a quadratic element. So usually we prefer using the quadratic element since it won't have any errors, while a linear one could have errors if it's a complex geometry. And also you have options such as local specification. So as I told you that in a mesh itself for a given component, not every mesh in the component will be of the same order. So you can go and localize. So for a given local area, you can go and define a different finer mesh or a more denser mesh. So that's up to the user if it's required for that particular way. So once you have defined the mesh, you have defined your mesh size and absolute sag properties, you can just click on mesh and your mesh will be created. Now that you have created the mesh, you can just press on OK. And the next step which we'll have to do is create a solid section. But before that, we'll have to shift back to our model app itself. So you'll have to go back to model from that drop-down menu itself. And we'll be creating a material now. So in this process, we'll be creating a material first, and then we'll be defining the solid section. So you can go and create a material. You can use so it's in setup. Okay, in setup, there's an option for create material. You can press on it, and you can select the type of domain which you want. It could be appearance, drafting, and simulation, and composite domain. So you can select simulation domain, give a title for your material, and we're not giving a covering material here. It's just the core material that we are going to define. So once you have defined that, now you will have to select the behavior which you want to apply. So here we are just giving an elastic behavior to it. So you can just select elastic from the tree, and you can give in the Young's modulus and Poisson's ratio. So once you have given that, you can press on OK. And now that you have your mesh defined, now you'll have to apply this particular, the material defined, you'll have to apply this material to your component. Now, how do we do that is you have to go onto the drop down. There's something called as material palette. So once you open material palette and you select the in session command, the material which you have created right now will appear onto the tree, and you can just drag it and drop it onto your either on your specification tree or on the component. So if it's not a complex geometry, you can directly do it for a component. But if it's complex, you might end up actually assigning the material for a different component altogether. So a tree will be a much more better place where you can just drag it and drop it on the tree, and then you can click on the tick icon. So that's where you can assign your material properties, and then your material will be added to it, and further you can create your solid section properties too. So now once you have defined your materials, your mesh properties, your solid sections, and you've also seen the procedure that is followed in order to apply all of this, we can move on to defining loads and restraints. So in order for a simulation to work seamlessly, you will have to define the loads and restraints. So loads is basically something that basically induces change in the model based on when it's applied on a model for a given amount of time. Now your load could be anything from a forces to pressures to apply translational to body loads or temperature. So any of these could be your loads which are applying to a given physical product. And the different types of loads which we have given you in the 3DEXPERIENCE platform by the Simulia tool itself is you can see you have different types of forces. You have force, remote torque, shell edge load. Then you have applied translational. You have different type of force connectors. You have velocity. You have centrifugal force, rotary forces, pressures. You have prescribed temperatures, centrifugal force, so inertia relief. So there's bolt loads and a lot more options are there. So based on the type of scenario that you're trying to generate or the type of simulation that you're trying to achieve, you can select any one of them from here and then apply it onto your geometry. And for any help, you can use the function command and try to understand what that particular load will be used for and how to apply it will be given to you by the help command there. Now coming on to, I'll just take you through a few forces and how to apply them. So for example, if it's pressure, so pressure is basically Newton per meter square. So in this case, once you apply a pressure on a given surface, the area of the surface is selected. So that's how you'll be defining a pressure. While force, you can either select a vertex, a node, or a common center point in the given model. So that is up to the user as to where the force is to be applied. And the unit for force that is being followed is Newton here. Again, remote force. So remote force is something which is, so the location where the force is going to be applied will be decided by the system based on your selection. So the total force acting will be selected. So you'll just have to given the total force that is acting, and then based on your selection which you have made, the force will be applied to it. Now, we'll be talking a little bit more about the remote forces, but for now, the shell edge load. So shell edge load is basically force per unit over a length. So basically, it distributes the force load over the shell edge. So these are for shell components where you can use this particular shell edge load command. Now, again, yeah, a little bit more about the load itself, the remote force. So if you select the total force and you want to apply it to a center point in that particular edge, What you could do is you can just apply remote force, and once you make that selection, it will automatically select the center point. And if you select all the four edges, then it will all the four faces of it. Then in that case, it will be the center force that will create. So based on so the system does it for you. It's generated internally itself. You can use this particular command if you require it in such a way. Because if you want to define a center load, you'll have to create a point there first and then link it to each of them and then apply it. So in that case, your remote force could be helpful for you. So that is one way you can use remote forces. Now coming on to a little bit more about it. So for defining a centrifugal load or gravity loads and rotary action forces, in this case, one thing that the user needs to note is while defining the materials, they'll also have to define the density. Because if density hasn't been defined, the gravity loads of the given component won't be able, the system won't be able to calculate it. So if you have defined the density in your material, your system will be able to calculate your gravity loads and your centrifugal loads accordingly. Since the mass factor comes in each of these terms, that needs to be defined. Again, your magnitudes of loads may vary with time during the step according to the amplitude definition, but the direction in which you have applied them will remain constant throughout the step itself. So there's no change in the direction that will be happening. Now, once you have defined the loads, that is the forces or the pressures that are acting on your model, you can go on to defining restraints. So restraints are basically defining boundary conditions. So a restraint could be anything from a clamp, a fixed displacement to a bolt load. So it could be anything. So for example, if it's a clamp, you can select a face, a edge, or a vertex, and all of the degrees of freedom for that component will be restricted. So this is what a clamp command is used for. While a bolt is something, since it's generally used in simulation, a specific command has been created for it. So you don't have to create all the mating surfaces and then create the bolt loads. So you can directly select the bolt load, select your bolt, and automatically the type of restraints that are to be introduced will be done by the system itself. And ball joint is one more one. So ball joint, instead of again going, so these are a few which are generally used. So the commands have been present there. So it basically mimics the behavior of a ball joint component itself. So if you have a ball joint model, then you can use the ball joint restraints. One more capability what we have is a multi-step simulation. So for example, if you are trying to do analysis on a tank, basically a compression tank or a pressure tank, and the pressure is varying with respect to time, it's not constant. So you can use a multi-step simulation there. So you can define initial pressure, and then for a given amount of time, that particular initial pressure will be acting onto your tank. And then eventually you can define one more point where the pressure changes to a different value, and then you can define the pressure values there too. So it will be a multi-step simulation that you could use. And this is helpful in order to do a simulation wherein you are encountering situations of these kinds, wherein two different types of forces or pressures are to be applied for the component. Now, selecting supports is basically the loads and restraints can be either directly applied onto a geometry. So, for example, if you have four different faces on which the forces, or if you want to clamp it, you can just select individually the four faces and then apply the load. Or there's one more best practice that is followed is creating a group. So a group, basically what it does is it creates a group for each of these places where a common type of uh, load or a common type of mesh or a common type of any reference that is to be generated. So in this case, if it is a load or if it's a clamp that you want to do for four different faces, you can select the four faces, create a group of it, and you can apply the force or the clamp command directly to the group itself. So in this case, it will be very efficient because if, for example, you have done any change during the assignment, you don't have to go on to you don't have to click on all of these components individually and apply. You can just select your group where the group one, and then you can just change the value there, and it will be automatically updated for all the four of them. So this is one very helpful way which you could do for a complex geometry. Maybe you could use this. And again, working with local coordinate systems. So the coordinate system is also important while you're doing the simulation. So if it's a force that you're doing, so the force can be applied either with the global coordinate system, or it could be with the local coordinate system, or you can specify the coordinate system in which you're trying to apply it for. So this needs to be taken care of when you're applying the loads. Now, initial conditions. So initial conditions are something that you start with when you're defining your model. So it could be either your initial temperature, which defines the initial temperature of the whole model. It could be the initial stress level. So if you're, so for example, if you know in spring suspensions, that is your monoshock spring, there's already some type of pretension that is present in the spring. So for example, if you want to take a note of it, you can use the initial stress command, and then your initial stresses will be defined. And similarly, initial translational velocity can also be defined for the components. So this was mostly all about the loads, restraints, and the initial conditions that you need to define in order to simulate a model. The next what we have is an interaction. So I'll just play the short GIF here. So interaction is basically used to simulate the contact between different parts of an assembly. So if there's a contact that is occurring between the different parts itself, then in that case, you can define the interactions between them. So in this example, if you can see, there's multiple strands of wire, and then it is clamped by the outer surface. Now, since each of these wires are in contact with each other, you'll have to define a contact in order for the simulation to be much more accurate and real life. Now, what is a contact? It's basically when two bodies are touching each other, a given amount of force will be transmitted. So that is, so if the wire at the top is pressed, it will further press the wire which is in the center or in the bottom. So to account for all of that, you will have to define your contacts in order for your simulation to be much more accurate. Now, in here, you could also define the friction properties. So if there's a type of friction, any amount of friction that is present between them, you can define these values too. And all of this can be done as well. Now, again, in contact, there's two different types of contacts that you could model. So you could either give a general contact or you can define the contact pairs. Now, a general contact is something wherein for the whole model, you'll be giving a general contact itself. So if it's the wire example, for example, you can just define the general contact, and the contact between each of these components will be defined by the common instance which you have done for general contact. While in contact pairs, so for each component that is interacting in a different way with the other one, you'll have to define a general a contact pair. So you'll have to go and select your main surface and your secondary surface, and then there the contact will be established for them. So the general contact approach. So basically, if you have a complex geometry, for example, this particular example which we have for the wire itself. So if you have to go and individually select it for each of these wires, the contact, it will be quite a lengthy process. So you'll have to select each wire and then associate it to a different wire as to establishing the contact between them. So it can be a very time-consuming process. So in that place, we use the uh, general contact, wherein the contact between each of these wires is defined generally. So the user does not need to worry about the contact that has been established between among them. So it's just the general contact which is applied. Now, the choice between applying a general contact or the contact pairs is with the user itself. So both of them are very accurate in their own ways, but it's mainly a trade-off between the ease for defining a contact and for the simulation process. So for places where you can or you are able to define individually the contact pairs, you should follow that. Else, if it's quite complex to define that, you can use the general contact option itself. For contact pairs, if you can see this particular product which we have here has two different parts which have a common contact between them. So in this case, you'll have to select a main surface and then you'll have to select the secondary surface. So there's an option provided in the window for them, and you can select it from there. Now, how do we define a contact? Here we'll see of how the general contact command works and the contact pair command works. So the interaction, so basically the option, if you can see the graphic, the first one is where you can define your general contact. The B option is where you define your contact pairs. And B1, so for example, if you have a geometry where you're not sure where exactly the contacts are lying, so in that case, you can use the contact detection tool. So the contact detection tool will help you in detecting all of these contacts that are present in the given component, and the user can directly select it from there and apply a contact between them. So The platform right now is very capable of helping the user. So it can show you the disconnected pairs, it can show you the contacting pairs, it can show you the intersecting pairs. So it will give you basically a visual feedback to the user in order to which type of contact they're trying to look for. So there is more types of commands that are present, which will help the user to generate these type of contacts very easily as well. Then the general contact command, so if you open it, you will have different types of options there. You can specify excluded surfaces, apply geometry-based correction, and apply stabilization controls. So what you can do here is you can either apply a general contact throughout the model, or what you can also do is, for example, if it's a few parts that you want to exclude from a general contact and you want to specify your own contacts there, you can just exclude them from the main general contact, and the options for them are also provided. So you can the support one and support two, the ones that are to be excluded, you can just select it there, and those won't be applied to the general contact. But for contact pairs, so if it's a surface contact, you'll have to select your main surface, that is your face one, and your secondary surface, your face two. So that's how you will be defining your secondary contact. Now, it could be either a surface to surface or a node to surface. So, the best practice which is followed is if you're trying to apply a pressure or if it's any stresses that you're trying to do, a surface to surface contact is more preferred because it basically averages out all of these nodes and then applies the load there. But you could also use the node to surface. It's not that accurate for this particular type of simulation wherein you have a pressure acting. It'll work too, but again, it's recommended to use a surface to surface discretization method. So the node to surface is something like a traditional approach, and the individual secondary nodes are connected with each other. Now, coming on to your contact detection tool. So what it does is it selects the whole model, and then you can give in a tolerance as to what. So the contact between different components will be different. So you can give in a tolerance as to where you want to define these contacts. And once you do that and you press find search pairs, it will find all the contacts based on the tolerance which you have provided. And then you can select from your this thing, the main tree itself, and it will show you where all the contact needs to be established and which of them is the main and the secondary pair. So the contact detection tool is quite helpful in that matter. But one thing that we have to note in the contact detection tool is the display settings may affect how the component looks. So the display settings on the tool itself, there are multiple display settings. So you'll have to take a look at it if the display settings are affecting the way your contact is working. And it'll also define a contact only if the two surfaces are approximately facing each other, and the two surfaces need to be very close to each other. So it cannot be like you have two surfaces which are very far apart, you can establish a contact. That won't happen. So you'll need something which is very close. These are a few things that you'll have to take care of when you're using the contact detection tool. So now that we have covered the whole basic setting up a scenario, your simulation aspects, your tool itself as to how you can basically generate a scenario, we can actually move on to creating a simulation process itself. So now what we'll be working on is an example which is like this. It's basically a buckle clip insertion model. So you can see the image on the right, which is basically a buckle clip, and you all might be aware of it. So when you're like putting your buckle, the buckle clip inside the buckle itself, you can see that there's some kind of stresses that the buckle has in order to for it to go inside. There is some kind of compression that happens in it, and that is what we'll be trying to simulate with the this particular example. So just to give you a few basics, this is how your action bar will look like. I'll recommend, since you're just starting up with the 3DEXPERIENCE platform, I'll recommend you to use the display icons and text. In this way, you will be able to know which particular command is for what. So it can be quite helpful for you to understand instead of trying to figure out the icons itself. Once you're well versed with it, I'm sure you'll be able to just look at the icon and decide and say what it is. But for now, we can use the display icons and text. So you just have to right click and select the given command. So what we'll be doing is we'll be creating and importing the content, and then we'll be working on it. So and we'll also be using the assistance panel, so it will give you a total feedback as to if you have done that given step or not. So that will be helpful for us. So this is the procedure which we are going to follow right now. We'll import the geometry. We'll create a mesh representation and mesh for the geometry. Then we'll be defining the material properties. We'll create a simulation process. And then at the end, we'll be executing the simulation and we'll save the data onto the platform. So this is what we are going to do. So I'll shift onto the platform right now. So if there are any doubts or anything, or if you haven't installed the applications right now, you can uh, ask us about it, because you will need the application at this point in order for to work on these simulations. Hello. Yeah, Dr. Dheeraj, are you there on the call?
Yes, I'm there. Yeah.
Yeah. So I'm not sure, because I've already shared the document with the students as to what files that they need to download, the applications that they need to download. So I'm not sure if all of them have downloaded or not. Could
No,
you
no,
check?
I think they have already done it. I think students, can you please mention if you have downloaded it?
Yeah,
Because
that
this
would be
was
helpful.
shared like on Thursday evening, I think, with them. Yes, sir. Yeah, Aditya is saying he has. Yeah, I think most of them have downloaded, so we can continue.
Okay, then that's great. So also I've shared you a document which is a My Drive file. So I'll show you how to use it.
Mhm.
So what you can do is right now follow the procedure which I'm doing on my screen. So you can go onto your web page itself, or your where you open your apps from. And now what you'll have to do is you'll have to go on 3D Drive. So 3D Drive is where I have uploaded a few files. So we'll be not be creating the physical product right now. We'll just be importing the physical product to the platform, and then we'll be setting up the simulation and the material properties for it. So you can go onto your 3D compass, you can open it and search for 3D Drive. So I'll just take a few pauses for you to follow up. So you can just open your 3D Drive component, 3D Drive application. So once you open it, just confirm me once if you have access to this file. I've shared it with you. Just let me know if you don't have it so that I can share it again. I'll just check the chat box once. So if you have access to it, you can mention yes in the chat box. If you don't, then I'll try to give the access to you. We have access, right? Okay. Okay. So what you can do is you can double click on this component. So there's two models here. So the first one, which will be mainly working for the structural part, is the buckle flip model. So what you can do is you can press on it, and there are two ways to download it. So you can either use the download option from here, or you can use this particular download command. So these are the two ways which you could follow. So once you download it, it'll, okay, so you can do show in folder and you can know where the part is. It's present in your downloads, and then we can import it. So once you have downloaded it, what you can do is you can go back to your platform and make sure that your platform is open. If you haven't opened it, I'll give you a minute or so and then we can start with it. So I'll give a minute to the ones who haven't opened their platform yet, so then we can go ahead with the actually importing the model. So I hope that you were able to open your platform. If you haven't, just mention it in the chat box, and I'll wait for you. Okay, so most of them I'm seeing that they have opened their platform. So now what you can do is you can go onto this plus icon and add new content. But the one thing you need to make sure is in the collab space that you're a part of right now, you have a leader access to. Just make sure that you have your leader access. And if you have it, then you can import a component. So just go on to import. So this kind of a pop-up will appear. Make sure that the format of the file that you're trying to import is a 3D XML file and the source is file on disk. Now what you can do is you can select the file you're trying to import. Now in my case, I have it in my downloads. So this is the model which I have. It's a buckle flip model and open. Okay, so your model is loaded here. Now, before you go ahead and import it, actually, there's a duplicate string option. Now, since there'll be an issue if everybody has the same file, what I'll recommend is you can use your name initials. So just use SP. So I'm using SP for mine. If your name is anything else, you can just use the first letter of your first name and the last letter. Basically, give a unique duplicate string so that there is no doubts about which model is yours and which is not yours. So once you've given a duplicate string, just press OK and your import progression will start. So once you have the model imported, then we'll open it. So we'll just wait for the model to be imported. And so just let me know if your systems are slower because the configuration of my system is a higher one. But if you have a slower system, it might take some time, but we'll wait for you. Okay, so the import is successful, the status is succeeded, and you can press OK. So this is how your import model will look like. And now it is in Innovia app itself. So what you will have to do is, I'll give you 10 seconds and then I'll go ahead with it. So once you have imported it, you'll have to right click on it and there is an open command option here. So all you have to do is just press on it and it will open it into a new application itself. So, okay, so this is how your model should be looking. So you have a female part, you have a male part. So your female part is the below one, so you can go and select it on the tree and see. And your male part is the one above here. So this is the model which we have with us right now. So for the ones who have completed this step, so now we can move on to actually creating a mesh and all of these things for this model. I'll just side by side check the chat window. Okay. So now what you can do is you can click on your 3D compass, and if you have the role installed, you can either search it from here, structural model creation. Let's do that actually. So we can just search structural. So you have a structural model creation application which is present here. So you can just search structural, or you can enter the simulation engineering role which is being assigned to you and search for this particular application. Now that we have searched it, we can just open it. Okay, so it basically gives us an option like this. So either a standard or an empty FEM. So based on whichever option the user needs to select, they can do that. So in our case, we'll go ahead with standard. And this is the second pop-up which will appear. So we'll let it be the main bodies, and the initialization method, we'll let it be to default, and we can select OK. So there's no changes that you have to do. So what it will do is it will create an FEM representation for us in the tree itself. Okay, so you can see that two tetrahedral mesh and two solid section properties have been created. So the mesh has these update options there, that is the mesh needs to be updated. So what we can do is, okay, we'll get the assistant command to, where is this? Just give me a second. So the assistance will be a little bit helpful if we have it. So I'll just quickly see where to access it from. So you can go into setup and okay, why is it not coming up? Is this on mesh? Yeah, touch tools. Okay, no problem. I mean, not able to find where the option is, but we can do it without that too. You can go onto your tetrahedral mesh. You can double click it and you can see that there have been mesh properties that have been assigned to it. So the support is the ordered geometrical set, which is created in this particular mesh, which we have. So your first mesh is associating to your, oh yeah. So if you can see the initialization has been done, you can let the initialization be as it is. You have the quadratic element selected and it's a tetrahedral mesh. So you can just click on mesh and it will generate. It gives us a warning signal. It mainly is that if there's any mesh that is final that is required, but as long as it does not generate any errors, it's fine. So as you can see right now, your female component has been meshed. So this is how your mesh will look like. The pan and the rotate options are similar to that of CATIA. So I hope you won't be facing any issues with it. So once you have generated, so you'll have to make sure that you press on mesh instead of OK. So you'll have to press on mesh, your mesh will be generated, and then you can click on OK. Now the next thing which we'll have to do is we'll also have to create a mesh for your male part. So you can just double click it. There's been an initialization done, and you can click on mesh. So again, a warning. Okay, so what we'll do is maybe we'll change the mesh properties itself. So we'll define the mesh size to 2 and the mesh sag. So the general method which we follow is we divide by 5 to the mesh size component which we have. So if we do 2 by 5, we have 0.4 is what we'll be defining the mesh absolute sag value, and then we'll generate a mesh. Sorry, 0.4. So 2 is basically the mesh size which we have selected. You can iterate this based on your requirements. But at this point, we have 2 and the absolute sag is by 5 the mesh size value. That is 2 by 5 is 0.4. We mesh it. Okay, the warning is again there, no problem. But we have a much more finer mesh in this case. Let's do quickly the same thing for the other one as well. We'll define it as 2 and 0. Okay. So you can let it be the one which it was already there, or you can change it. There might not be any issues that will happen, or you can define a much more finer mesh. Okay. So now what we'll be doing is we'll have to create a material right now. So we'll start by creating a material. So the option which you can use is you can go back to your model, and then you can go into your material command here, which is in setup. So you'll have to go in setup and material. So in material, you can select the type of material which we are trying to create here. So you'll just have to go create material, and the material which we're going to apply for them are the same. For the male part and the female part, we are going to apply the same material. I'll just check the chat box if anybody has any issues. Okay, nothing. Okay, so you can rename the material again. Again, start with your initials and then define the buckle model. Anything you can name it to based on your requirement. You can just name it anything. Now, again, as we discussed about domains, there are three domains here: appearance, drafting, and simulation. So you can just select the simulation domain in this case. For covering materials, we haven't selected anything. So there's number of materials is 0. We'll create only one material, that is the core material. And you can just press on OK. So you'll have to only select simulation domain, name a material, just take your initials and click on OK. So now it will open the 3D search itself. But so you can either see the given material here, and then you can open the simulation domain. But in my case, since the domain has already opened up, it's basically opened up here. I can close it, For the ones whom it hasn't opened up, you'll have to right click on your material which you have created and then go on to simulation. Open the same simulation domain here. You can close it, and this is what my simulation domain looks like. Now for this material, since it needs to be elastic in its behavior, so what we'll have, and there's no permanent deformation that is happening based on the loads that we apply. So we'll just go into structures. There's abacus multiphysics. Then you can enter mechanical and elasticity. Okay, so I'll repeat again. It's in structures. You'll have to just press on the drop down. Then you'll have to go into abacus multiphysics. Then you'll have to go into mechanical. And in mechanical, you have elasticity. So now what you can do is just press elasticity like this. So all of it will be arranged out here. And you can just expand it a little bit here, and we can give in the Young's modulus values. Okay, so the units will automatically be added if you delete them by any chance. So 2 e power plus 0.009. This is basically 2 into 10 power 9, the value which we are assigning for the Young's modulus. So E can be used there. And once you have defined the Young's modulus, the Poisson's ratio will be 0.394. Okay, so I'll give you a second, and you can just repeat this process. So it's in structures, abacus multiphysics, mechanical, elasticity, and elastic. So you'll just have to give in the Young's modulus and the Poisson's ratio values. So once you have done that, you can just press on OK. Okay, so now we have created a material for our component. The next thing which we have to do is apply this behavior, apply the material properties to our components. So we'll just again go on to this material command here, and we'll use this arrow, which is the drop down menu, and we'll go on to material palette. So once you open material palette, as I told you, there'll be options there for all, recently applied, and end session. So since I could just go and filter it from here or search it, but it might be a little bit tedious to do so. So what I'll do is I'll just go into in session. So as you can see, I have the material which I've created right now. It's SP buckle material. So what I can do is I can just click on it, I can drag it, and I can apply it to my physical product here. And you can just drop it. And you can see there's a tick mark that has come here. So you can just click on tick. And now if you open it in the tree, you will have the material which is applied and the simulation domain here. So this is how simply you can apply the material properties. Now you can replicate the same for the other material. Just click on it, drag, or since we have done for the mail, right? So what we can do is either we can drop it onto our component itself, but in this case, it will be associated with the mesh. We'll do it for the mail component. And again, you can see the material has appeared. You can click on this tick icon. Now you have the materials defined for both these buckles. So once you have them, you can close your material palette. So for the ones who need one more time, so you'll have to just click it, drag it, and put it on your physical product. That's how simple it is. And you can close your material palette here. So now that you have your materials defined, we can go on and define your solid sections. And since we selected the automatic one, we have the solid sections already present here. If these weren't present, okay, I have to show you that I'll delete the second solid section so that I'll be able to explain. Okay. So what you can do is enter solid section 1, just double click on it. So you can see that the selections have already been made. So ordered geometrical set 2, and the material, since it was directly associated already itself, you have the material defined here. And in orientation, you can specify the orientation which you want, that is the axis around which the material has been applied, the rotational, and all of these properties can be defined. But these are for more complex situations, so we'll not go more into it. So we'll just apply. So right now the solid section has been defined. So what I'll do is I'll delete the solid section and I'll show you how to create a solid section. So I'll delete the one that has been created. Now what you have to do is you can either do this or you can just do it as it was done earlier. So you can go into properties, you'll need to be in your model part, and you can select solid section. Now it needs a support and a material. Now, since it's the male part which I have to try and create a solid section for, I'll just select it here and I'll select this order geometrical set too. Okay. And since the material has already been assigned, the material properties are already present and I can just press OK. So I have a solid section 1 for the female part and a solid section 3, which is the one which I created right now for the male part. So this is how you can define a solid section. So if anybody has any doubts, you can put it on the chat box and I can help you with that there. Okay. So I'll just quickly repeat it once again. You'll just have to double click once you have the material applied and the material will be there and you can just press OK. And now what we'll do is, as you can see, there are these options here, like these uh, update messages that you need to update. You can just click on update, it'll update and you can see it will go off. So your whole assembly right now is updated with all your mesh and your material properties. Now the only thing left for us to do is basically defining the loads and the restraints which are going to occur here. Okay, so this is all that you'll be mainly doing on your this thing, the meshing aspect. Now to actually generate a simulation scenario, you'll have to change the application. So you can again go on to, just make sure you select your root product. Just double click on your SP buckle.default, just double click it. Make sure that you are on your root product and open your compass and you can search mechanical scenario creation. You can see there are different types of applications here. What we'll be mainly requiring is the mechanical scenario creation app. So you can go on to mechanical scenario creation app, just open it. It will change the application now inside the platform itself. And you can see there's a different type of analysis that you can do. So you can do either a structural simulation, you can either do a thermal simulation, or you can do a thermal stress type of simulations. So for that you can use the thermal structural analysis case. So for our use case right now, what we'll be doing is for a structural simulation. For the next session, we'll be using the thermal one. So make sure it's selected to structural and you can press on OK. Okay, so right now, based on the selection which you have done, these paths will be selected. Now just minimize it in your tree, the components which are open. So basically a simulation consists of a model, it consists of a scenario, and it consists of a result. So scenario is where you will be defining your steps, your interaction restraints, the contacts that are there, the loads that are present. So all of that is done in your scenario. And your model part is your where your 3D model and your meshing aspects are present. That is your material properties and all of it. So for the ones who have opened it right now and the ones who have any doubts can post it in the chat window with anything and I'll help you again with the process. So right now what we did is we shifted from your mechanical structural creation app to mechanical scenario creation application using the compass itself. So you could see how seamlessly this was done. So we had the model, then we defined a mesh, and then we are now on the simulation aspect. Now, before we actually go ahead with the simulation, you can see that there'll be a small icon like this, which basically shows structural analysis case and no procedures exist, right? So this is where we start with the simulation process. So now we have to go in setup, and you can see, so for a simulation to go ahead with, you'll need an FEM model. And since you've already created the FEM model, it hasn't been associated to this analysis case. So if you go into setup, there is a finite element model here. So just click on it. You'll have this particular command which is opened up. So remember I've told you that you could have multiple instances for an FEM. So you could have about 10 different type of FEMs that you could generate in a given model, but at one point you can use only one. Now here you can either select an existing one, that is this one which we have created, which is the same here. So this is the one is what is represented here, or you could create a new one. It's up to the user and the type of mesh that you want to create. So if you select it, you can just select and you can click on OK. So right now, if you can see, there's an exclamation mark, but this will change to a tick mark. So once you have defined the FEM for the given simulation, it will automatically get converted to a tick mark here. So the next process which you will have to do is define a procedure. So procedure is the type of steps which we follow. So based on the type of simulation that we are trying to do, we'll have to select a given step here. So we can go into procedures. I'll just quickly repeat the structural analysis case. So you'll have to go into setup, finite element model, and select the FEM mesh which you have in your tree, but it will be displayed here. Now that you have created that, we'll enter into procedure, and you can see there are different types of steps here. So for example, the one which we'll be requiring is static step. So right now, if you can see, I just hovered over it and it shows me configures a stress analysis procedure of a stable problem in which inertia effects are neglected. So this is a basic one. Then we have quasi-static, so configures quasi-static displacement analysis procedure with time-dependent material behavior. So if the material behavior is changing with respect to time, then you'll have to select a step like this in order to have a much more accurate simulation. And so on and so forth. We have static perturbation, bulk, and like I told you, if you want to explore any of it, you can just click on F function and F1, and a window on the right side will pop up. So it's just loading right now. So if you can see, a window just popped up on my screen, and it will give me an explanation about the basics, a little bit brief explanation about what this particular function could help you with. So this is what is with static perturbation steps. You can just read through it, understand. But if you need more information, this is where the help command, and you can go to user guides. So this is how you can do it. Okay, so now let's close. Okay, our step has come up here. What we'll do is as you can see right now, the assistant has just come up here. Just see if you have it too, you'll need it. Like just go onto the right side and there'll be an arrow pointing out there, something that will look like this. If you just go and press on it, it will come up and you can pin it to your screen. Okay, so right now you can see that we have our paths, that is our model present here, and we have our mesh associated with it. But there's no interaction, no connection, no restraints, no simulation, no results that have been generated right now. So for our example, what we'll be needing is a static step. So you can just select static step here. So you have multiple options here which we'll have to fill in. So the initial time increment in our case will be 0.25 seconds. You can replicate it as I do it. So there's an initial time increment wherein you'll have to give it 0.25 seconds. Then the minimum time increment, you can let it be as it is. And the maximum time increment would be 1 second. So you can let all of that be like that. Then you can enter into stabilization, and the stabilization type you can select to energy fraction. So there's many other ones. If you can just press on it, and you can see that there'll be a little bit of explanation on what stabilization type is basically. So you can select that, and the energy fraction value we let it be to this one. If you want to understand what it is, it's basically the dissipated energy fraction or used in automating the dampening algorithm. So this is a backend solver details that you need to fill in basically. And the next thing we'll have to go into is advanced. And you can see that it is include geometric nonlinearity and matrix storage solver default. So you can let all of these commands be like this. So make sure you select your stabilization type as energy fraction. And also you change the initial time increment to 0.25 seconds. So these are a few things that you will have to do. Make sure you have done that, and you can click on OK. I'll just let it stay for a while for the ones who are doing it. But once you're done it, you can just click on OK. So let's click on OK now. So we have a static step, and you can see the static step has been created. Again, there's multiple steps you can create for a simulation. So that will, if you're trying to iterate the process, you can do that. And if you can see the assistance right now, the setup has also been completed. So now what we are left is with connection, interaction, restraints, and loads. So the next thing what we'll be doing is defining the load values. So what we can do is, the interaction part. We can go into interaction, and for this example, we'll just define a general contact since there's only two products and there's no specific type of a surface-based contact that we want to do. We'll just go into general contact, and you can see like all surfaces, include all surfaces basically which are present here, and apply geometric based contact here. So you can see the global contact property which needs to be established. So you have again option. Okay, we'll be selecting the default one itself. And once you do this, you can just press on OK again. So you can go in each one of them and change anything that you want. These things, if you want to exclude any surfaces, if you want to like the thickness assignments, the vertex assignments, edge criteria. So all of this can be done based on if you want to include them in your simulation process. So once you have the general contact, you can just press on OK and you can see it has been updated. The connections and interactions have been defined. So now that we have done with that, we can go and define our restraints. So in this particular example, if you can see what our objective is to achieve is the buckle, that is the that is the male part, which is the orange one, is entering the female component. So in this case, we just want to see the deformation that is happening in that case. So what we'll be doing is we'll be fixing or clamping this male component to the bottom itself. Oh, sorry, the female component. So we'll just go on to restraint, and there is a clamp option here. So if you just hover over it, it prevents a surface from moving or deforming. So we'll just rotate our model, and you need the bottom part for the female component. So you'll just select clamp, and you'll select the face here. You can see the face has been selected. So that's how you do it. If there's multiple faces, you can go and select a group in which you can do it. But in our case, it's just one single surface. So we'll select it from the geometry itself. So I'll just repeat again. You just have to go on clamp, select the face. So once you've selected the face, you can click on OK. So you can see the restraints for this has been introduced. Now we also need one more type of restraint that we have to establish here is we want this particular component above here to go inside the component which is shown below. So for us to do that, for us to establish that kind of a movement, we'll need a fixed displacement and the movement should not happen in any other axis. So we need the component to be moving only in the z axis. The component, if it starts moving in y or x, is not something that we want. So we'll just go into fixed displacement and we'll select the top surface of this component. So I'll just zoom in a little for you to know. So you can see the surface, you'll just have to select it. And you can see a face has been selected. And right now, as I told you that we need the motion in only one direction, you can, so once you select, so if you hover over the translational X, it prevents the geometry from moving linearly in X direction. You can just select this and select Y. So what this does is it clamps the body from moving in any of these axes and only a linear action about the Z axis is possible right now. And the axis system, we'll keep it to global since we haven't defined a local coordinate system here. And the global Z is basically how this is going. And we can press on OK. So what we've done right now is we have defined a clamp for the bottom section, which makes sure that our component cannot move and the female component does not move anywhere and the male component has only one direction in which it moves, that is downward. So once you have all of this defined, the next part is what we'll be doing is we'll be applying a translational motion to our male component. Okay, so if you can see the assistant, it is telling me that the loads haven't been defined yet. So I'll go into loads and you can see there's various loads that you could choose from based on what you require. There's pressures, there's different type of pressures, there's forces, there's again different type of forces. You have bolt force, you have applied translational and a lot of them. So what we'll be requiring is applied translational. So what we'll do is we'll just select the face, the face which we selected earlier. Since we want this component to be moving in the downward direction, right? So if you can see the arrows right now are pointing upwards. So, but we want to go it into negative. We want the component to be moving in negative Z direction. So right now what you can do is you can give a minus 18 value. So the buckle length, which we do, so the buckle, the male section needs to go down by 18 mm. So if you just press on 18 mm and you press anywhere, it will automatically be updated on your component too. So right now, if you can see, there's a minus 18 mm translational that will happen in your component. And there's nothing else that you need to define. Just the face. You need to select the top face for the mail component, and you can click on OK. So I'll wait for a bit for the one for you to replicate it. Yeah. So once you have done it, you can just click on OK. And right now we have the translation as well as applied here. So if you can see the assistance here, the setup has been done. That is your static step. Then you have the parts, that is your main model is present. You have the connections, that is your general contact, and interactions is also the same thing. Then you have your restraints, which is the clamp and the fixed displacement which you have applied. The load is basically the translational motion of the mail part, and the meshes have also been done. So the only thing right now left is to simulate it. But before we do that, I'll just show you how the scenario uh, component also looks like. So if you can see, you have the interactions present here. So there's a general contact. The restraint has the clamp and the fixed displacement. Then your load has the, uh, just take it down a bit. Yeah, applied translation. So this is how this will look like. And now that we have all of it created, what we can do is there you can see there is a simulate option here, right? So simulate, basically what you can do is there are three options again below here. So you have model and scenario checks. Basically it checks for any, it does not simulate your model, it will just check for any errors or anything that you have missed upon. So if it's a very complex simulation that you're trying to do, you obviously do not want the simulation to fail in the end just because of a fail step. So model and checks is a short way of doing it, or the assistance option as well. So it will just basically check your whole model, update it completely, and check if there's anything missing, if any material definition or any mesh has not been given to a component. Everything will be done by the model and checks. And simulation checks is also on the same lines. For simulation to run, it will just show that the simulation is ready for running right now. What we can do is, since all of it has been set up, we can just use the last option, that is simulate. You can just click on it, it will load for a minute. So it might take some time based on the system that you're using, but yeah. Till then, if anybody has any doubts, they can put it on the chat box and I can help you with that. Or if you need any step to be repeated, I can do that.
Hi, Siddharth. Good morning.
Yeah, hi, Lotso.
Good morning, everyone. Good morning, Dr. Dheeraj. So, Siddharth, sorry to interrupt you. Once this example is over, what we can do is you can engage students more. Like ask them voluntarily who wants to kind of volunteer, and
Right.
whoever want to volunteer, make them, completely do this process once again. And during the meantime, if students have any questions, they can ask you.
Sure,
Okay, and you can
yeah.
clarify their doubts.
Yeah, we could do that too. Yeah.
Yeah. All right. Thank you, Siddharth.
No problem. It's taking quite some time. So if you have the ones who have the simulation ready, can just press on OK, and then the simulation will start for you.
Go sit there. Oh, sorry. Hi, Lord. Good morning. Welcome.
Good morning, Dr. Dheeraj.
Yeah.
Okay, so what we can do till then is, I think there's some issue with my system. So if anybody who wants to volunteer, so we can, I think, do that part right now. This might take a minute or so for it to simulate, I think. Mm, So actually, let's do that. I mean, oh yeah. So Dr. Dheeraj, are you there?
Yes, yes, I'm there.
Yeah. So I think what we can do is, as Lloyd suggested, we can have somebody from the audience right now and have them share their screen, and
Yeah,
maybe
sure,
we can try to replicate the process on their system till my
sure,
system
sure,
starts working. Yeah, we can do that.
sure. That will be helpful. Yeah, Dharmendra, can you allow students to speak and share the screen?
Yeah. So if anybody has any doubts, they can feel free to ask me. I can help you out on your screen, and we can replicate the process as well.
Okay, students, is it getting complex or something? Come on, give us a honest feedback. You feeling it a bit complex? We can go a bit slow. In case if you are still not able to understand or something, you can let us know.
The
So
one
I'm
who
not able
want to
to see
share
much
its
of the
screen
chats.
can raise their hand so that I can make him as presenter.
Yeah.
Also, everyone is on unmute, so the one who want to talk can talk. Everyone is allowed to talk with the presenter.
I think most of them are facing an issue with the system being slow to respond to the platform, I think, for the simulation. Oh, no problem. If there's any step you want me to repeat or anything, or I could take you through the whole process again, we could do that. There's no issue with that. So if anybody needs any step, they can put it in the chat box or unmute and respond as well.
That what is the average time required for your simulation to run?
Actually, I think I did a selection mistake, so I'm just quickly rectifying that. It shouldn't take long, actually. It should take, on my system, it takes about 5 minutes or so.
Mm-hmm.
It's the time it takes, but I'm not sure how fast it'll be on their systems.
So what's the status at your end?
Oh yeah, my model just loaded again, so I'll just define the properties and I'll simulate it.
You can
I
present your
need,
screen, Siddharth.
oh sure, I could do it.
You can present your screen and just speak about what went wrong and what you're trying to fix it.
Mhm.
All right, yeah. So in the meantime, even if the system is slow, they can have a look at the screen and try to understand the process. So also, I strongly suggest students, in case so very detailed solution, I am it's very step by step. In case you're if you are not able to remember it, what you can do is take a notes and as well, you always have access to this learning resources where you can go and do it. Don't feel like it's very complex. It's very easy, provided you spend some one day or 2 day. Once you start learning the course, you'll be much finer.
Okay, so since I just reopened my platform and the restraints and loads have been removed, so what we'll do is we'll actually replicate this process again. So right now, if you can see, the restraints and loads have to be defined. So I'll just do that again. So I'll go on to clamp. So clamp is basically I'm trying to restrict the motion of the female component. So I'll select the face. The face has been selected. That means this particular component won't have any degrees of freedom and it won't move right now. So I can press on OK and the bottom face is clamped right now. The other thing which I need is I want the top component, that is the male component, to be moving in translationally downward in the Z direction, right? So for that, I will use the fixed displacement option, wherein once you select the fixed displacement option, it will restrict the motion of a component in a given axis that you've selected to. Now, it could be either rotational or translational based on the type of scenario that you're trying to generate. In our case, we'll restrict it to translational itself. So what I'm going to do is I'm going to restrict the motion of the male part to only downward Z direction. So for that, what I'll have to do is I'll just select the surface, which is the top surface of this component. And in the translational, I'll restrict the X direction and the Y direction. So right now, the motion of this particular component will happen only in the Z direction right now. And this is how I'll be defining the fixed displacement, and I'll press OK. So once I have the displacement, also the restraints defined, the next thing that I'm left with is defining the load. Okay, so for the load definition, what you'll have to do is you can go into loads, and in loads, as we've already discussed, there are different type of loads that are present, and you could use any of them based on the type of scenario that you're trying to generate. In our case, we want the male component to be going downward by a translational of about 18 mm. So we want a motion of about 18 mm for the male component. And what we have to do for that is we'll select apply translational, select the surface that needs to go down by 18 mm. And at this point, if you could see, the direction is upwards right now. It's not downwards, it's upwards. So to do that, I'll just enter a negative value and that will automatically change the behavior. So I'll enter minus 18 mm for my particular component. And if you can see, the change has automatically happened in the model too. So you have the component that will go minus 18 mm downward. There's no other change that you have to do in the model right now. And once you press OK, the change will happen. So right now what we have established here is the female component is going to be applied on this component. So what we can do is we can simulate it right now. And let's see how the simulation results look like. Okay, so somebody is asking absolute sat. So I think somebody has answered that already. Yeah, so Saurav has answered that. It's basically the maximum gap between the mesh and the geometry. The maximum distance is what the mesh sat is. And usually it's divided by 5, the value of the mesh size which you have defined. Okay, so right now if you click on simulate, this is how the window will pop up. So it'll use a number of cores, and these are all things that you don't need to bother about. You'll just have to click on OK. And now we'll have our model start simulating. If you can see this pop-up which appeared here, preparing simulation for execution. So right now it will try to simulate the model which we have created here. So any warning signals, any errors can be shown here. In iterations, we'll have all these steps that it is doing in order to achieve the simulation. So it'll take about 5 minutes, and then we can have the simulation ready, and we can see how to analyze the results in a simulation. Yeah, so we'll just let it simulate, and any messages that are generated, so for example, warnings. So as long as there's no errors generated, there's no problem to it. But any warnings, you can see that there have been 4 elements that are distorted. So these can be reiterated. You can define a final mesh based on wherever these stress concentration zones are. So that all could be done, and you'll have quite a few warnings that are generated. You cannot avoid that because while the simulation process goes on, you'll have some types of element that are distorted based on the geometry of the component itself. So what we mainly need to see is if the simulation is happening and if the results we are trying to achieve are validated or not. So we have the simulation done for about 25% of the simulation is done. So it should take around 3-4 minutes more, and then we'll be able to analyze the results of the simulation. In the meantime, if you have any doubts or if you haven't been able to replicate a process, you can put it on the chat box or maybe unmute yourself and ask us about these questions too. Okay, so for the application which we are using currently, there's not a web-based application for it. It's a platform application itself. So this you'll have to use the application, but you can analyze these results using the web pages. That is your widgets. You can analyze these results. But for simulation, you'll need the platform applications itself. At least for this role, there are platform applications. For other, we have the web-based too. So we have about 37% of it done. So these are the step times basically, and the total time, and then we have the time increment that is occurring in each step. So you have the whole process which is mentioned here for the iteration of the different steps. So about 50% of the simulation has been done. So it might take about 2 to 3 minutes more, and then we can analyze the results. So the messages, as you can see, the warning signals are about 13. There's no issue with it, mainly in terms, as long as there's no error generated. If there's an error generated, then the simulation won't go ahead. These are warnings related mainly to your algorithm or the backend solver which is there, and the type of mesh that you have defined. If it could be a more finer mesh, that is what it is really pointing out to. So if you can see excessive distortion at total one integration point in the solid. So these are quite few errors that are generated, but yeah. 62% of it is done. So this is your whole simulation process, which is in the diagnostic files. You could read through them and understand more about what is going on in the backend part. Okay, 79% of it is right? Yeah, 97. Okay, so we'll have our results opening up right now. Yeah.
Siddharth sir?
So the yeah.
Yes, sir. Can we have any training content or tutorials regarding these things so they can do study on them in meantime?
Okay. Okay. So yeah, as I mentioned that you could use the, okay, just before that, the results are like being extracted. Okay, so I'll just quickly go through the simulation and then I'll help you with the resources where you could use it from. So this is how your simulation is. You can close it. So if you can see, the model looks something like this after the 18 displacement. So we can play an animation for it and analyze of how this is happening. Now, since it's going a little too fast, what we can do is for the ones whose simulation is completed, there's these three dots which you can find here. And there is a stopwatch type of an icon. You can just click on it and you can change your speed of the simulation that is occurring here. And maybe you could reduce the speed down to something like 8x. That should do, I think. So the simulation will be much more slow. Okay, we'll reduce it further. Okay, so now you can see that there's some kind of stresses that are generated in this portion when the buckle is going through the female part. So there's some kind of reflection that happens, but since it's not really visible, it's hard to see what exactly is happening here. And this is the von Mises plot here. Now there is an option which Simulia provides for you to, in order to analyze these results better. So what you can go do is go into display, and there's something called as plot sectioning. So what the plot sectioning command basically helps you do is to basically cut the view out of, and like you can actually go into a component and see how the simulation is working. So we can see right now the plot sectioning has been selected here, but I can select it to maybe the inner component that is here. And if you can see right now, I'm able to see of the stresses that are generated inside due to this plot sectioning. So it basically is removing the exterior part and actually showing you how these results look like. So if you can see right now, what is happening is when the buckle is going in and establishing a contact here, the buckle is pressed inside, and thereby there is a kind of force of the stress is generated in this particular part of the component. And the variation of the stress, you can see it here on the plot, which is here. And then you can also compare the deformation of the body. So for example, if you go into deformation and you also select this, so you can see that the deformation that is occurring in the component when it is going through the buckle itself. So this is just one of a few simulations that you can generate using these applications, but there's a lot more that you can do based on the type of results that you're trying to obtain. Okay, so now what we have is we have the undeformed model, which is on the background, and the deformation that occurs. So if I play this, you can see the undeformed model is there and the deformation that occurs when this particular process is being done. You have various plots that you can do. You could do a von Mises stress, you can do a contact pressure, contact shear. So any of these results can be analyzed by the user. So we can stop the simulation. You could shift it back to von Mises stress. Now, if you want to know where the maximum and the minimum points of stresses are, what you can do is you can just right click onto the component and you can see there's an option for show minimum and maximum values. So if you press on it, it gives an option for like this, where the minimum stresses are generated and the maximum stresses are generated. So you can see the points are moving, that the global maximum force that is occurring at this particular stress concentration zone, and the value of it is fluctuating from about 0.0348 to about 8.92 Newton per meter square. So this is how you could analyze your results, understand about the simulation that you're trying to achieve here. So that's mainly with the structural simulation. Now, if anybody wants to volunteer, we could do it on their system. And can we do for factor of safety also? Yes, you could do for a factor of safety simulation. You could add it to your material properties, and you could increase the load as well. And then you can run for those kind of simulations too. So anybody from the audience who wants to display their screen or share their screen, and we could replicate on their screen too, we could do that. If anybody is volunteering, or if you're facing any issues in your system at all, we can help you with those as well. So just let me know, and you can put it in the chat box, or you can just raise your hand, and we'll be happy to answer your doubts here. Oh, hello, Lloyd. So are you there in the session? Or
Pardon?
Tell me.
yeah, I mean, so I don't think most of them have any doubts, or I'm not sure.
No problem. In that case, we can proceed to the next session. Provided,
Yeah.
can you please, Siddharth, in the EduSpace, is there any learning resource available for this particular
Right,
module
right.
to show them?
Okay, I'll do that quickly too.
Just walk them
So,
through. So even if if they have some difficulties later, they should be able to just go through the course and
right.
learn it.
Okay, so what you can do is, as I told you, that there are a few courses and contents that you could use in order to understand these applications. So you could go on to User Companion, and it'll take you to 3D Experience EduSpace. So what you can do after coming here is log in with your credentials that you have. So I'll just quickly log in and point out to the course that you could use. I'll also put the link for the post in the swim communities or in the chat box, and you could go to that particular course content and maybe try and understand a little bit more about the type of the simulation apps, the other applications that we have. So I'll just quickly log in. So once you're in here, you can go into Learning Catalog, and you can select the brand. That is, this particular brand is the Simulia brand which we have. So you can go into Simulia, and you could select the role, but if you just scroll down a little here itself, you can see the different type of courses which are present here on which you could work on. So for understanding more about the structural simulation, the course which I'll recommend you is the Perform as a Structural Mechanics Engineer. So if you click and open it, it has a complete process for you to understand how to design, like start with your modeling and then your simulation aspects, how to define your loads, restraints, meshing, material and section properties. So it's about, it has about 11 contents and about 40 hours. You really don't need to do the complete course, because it has more detailed analysis towards the parametric design study app than complex components. But for the ones who are interested, can definitely go through the whole course content and learn more about it. So you have the thermal simulation also a part of it, as well as the structural simulation. So what I'll do is I'll just copy paste this link and put it on your chat box. And now that you know how to access it, you can go and access it from your 3D Experience platform too. Not sure if the link has come as a link, but you could just test that, or you could use the procedure which I've shown you in order to use this particular course content. So yeah, I think that's all about the structural simulation. So Dr. Dheeraj, do we take a 15 minutes break right now, or do we proceed on with the
Sure,
next
sure,
session?
sure. I think we can start after 15 minutes. No problem. At 11:45 we can assemble. I think we should have.
Sure, yeah, I think that should be great too.
Yeah,
So in the
sure.
meantime, if anybody is trying to replicate the process and have any doubts, they can put their doubts in the chat box, and we can connect at 11:45 and we can discuss on them, or we can proceed with the thermal simulation aspects as well. Okay, so yeah, let's take the break then.